In this video, we're going to extend our discussion of stepwise stability constants, and we're going to look at a related topic, namely the lability or the kinetic behavior of coordination compounds versus the inertness or the thermodynamic stability of coordination compounds. Okay, so there's a variety of compounds we could use to discuss this, but the ones that I think will make a nice point are, for example, if we take this equilibrium, it's this equilibrium of nickel 2. I don't like the way that plus was obscured. Nickel 2, aqueous, and for cyanide ligands, aqueous, and this can be in equilibrium with the coordination compound. Okay, so we formed this coordination compound here. And we can say that K here, so we drew K would be, so here's the equilibrium constant here, K would be the concentration of the compound. So take the concentration of all of that stuff, which let's say is aqueous, and then we've got the concentration of our beginning nickel, and then the concentration of Cn minus to the 4th power. Remember that the coefficient becomes an exponent in this equilibrium expression. And this value is very large. It's about 10 to the 30. So we would say that this complex is very stable. Or thermodynamics favors product formation. But scientists have used radio-labeled carbon. They've essentially radio-labeled the carbon in the cyanide ligand here to look at ligand exchange. So here it's stable, but it's labile. So let's see why this stable compound, stable because the equilibrium is shifted hard right. It's labile because it can undergo the following ligand exchange. So we can take Cn for 2 minus, aqueous, and then when fed with here the asterisk means radio labeled, so carbon 14, which means radioactive. Then it will produce the radio-labeled coordinate compound. Minus, and for the original Cn minus, aqueous. Okay, so it's stable, but it's labile. So that means it's a stable structure, but the ligands can exchange. Remember, equilibrium is a dynamic process. Okay, so remember that equilibrium is a dynamic process. So at face value, these labels seem to be opposing, but when we remember what is actually happening in equilibrium, then we can see that they tend not to clash in what they say about the structure that much upon second inspection. Okay, let's look at another example. Okay, let's consider another example. So now let's have a cobalt compound. And we can add in the presence of acid, so 6-hydronium, and we can get cobalt Hexa Aqua ion, and 6 ammonium ions. So basically a total ligand exchange. Now, if we write the K value here, so let's say we have a K value here, well, K would be this chemical, the Hexa Aqua ion, concentration of that, and then ammonium ion to the 6th power, because there's a coefficient 6, and then we have CO and then hydronium 6th power. Okay, and this is roughly equal to 10 to the 20. So again, it's very stable. Stable because it's a lot larger than 1. Or rather, this product, the product is stable here, so the numerators are stable. So obviously, this is the stable product, and this would be unstable, right? Because the K value favors formation of product, therefore the reactants are less stable. So it's unstable, but we're going to see that it's inert. So inert, this seems like an oxymoron. Unstable here sounds like we're saying it's reactive, but inert means not reactive. So not reactive. So when we say unstable, we don't necessarily mean reactive, because here we have something that's unstable, but it's not reactive. So let's see. Very, very slow ligand exchange. Okay, I don't have any numbers to offer you, but I know that's very, very slow. So if we compare the last two slides, we're looking at a labile compound versus an inert compound. So we've definitely talked about reactive, not reactive, where this has got nothing to do with stability, right? Because here we saw that you can have something that's unstable, but it's not reactive. So it's important to point that out before we start to conflate the two. Okay, so that's the first thing I wanted to point out in this video, to keep us aware of that. Next thing I want to look at, so let's get a new slide. Next thing I would like to look at is, what would I even call this? I want to go back and continue looking at stability constants. So I guess we'll call this, actually, do I want to look at that now? Maybe not. I was going to look at something called the Jahn-Teller effect. Don't think we want to look at that just yet. So let's do something else. Never mind. Okay, let's go back then and look at, let's see, do we want to look at titanium? I was going to look at some notes on titanium with you. Just have to find where I put my notes. Nope. Now I can't find them. Okay, well, at least the immediately next thing I wanted to look at, I guess, while I save a bit of time, is inner and outer orbital complexes. So let's do it in black. So inner versus outer orbital complexes. Inner versus outer orbital complexes. Let's look at, I don't know if it matters which one we look at first. Let's look at cobalt with 6 ammonia ligands and a 3+ charge. Now, we know that ammonia has no charge, so these 6 ammonia don't impart any charge. But we know that there's a 3+ charge overall, so it lies squarely on the cobalt. So we have cobalt 3+, and we know that this is a D6 complex because it has 60 electrons. So cobalt, we know, has 27 electrons. So it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, so let's see what we've got, 2, 4, 10, 12, 18, 20, so 3d7. So that would be cobalt. But cobalt with 3+ charges, I've got to lose these 4s. So I would lose those two first, and then I'd lose that. one of those. So this would be 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. So this is why we're saying it's a D6 complex. Okay, so we have this complex. Now we have to form an octahedral field, or an octahedral field has formed, but we need to explain that. So from valence bond theory, we might expect sp3d2. This would be an outer orbital complex. But what we're going to consider now is we can have D2 sp3, which is what we mean by inner orbital complex. So essentially, if the D is on the left, it's inner. If the D is on the right, it's outer. So which is it going to be? Well, in this case, let's get rid of that. Really hard to talk and draw at the same time, at least for me. Okay, here, the NH3 ligand, which is the ligand responsible for causing the octahedral field, is strong enough to cause pairing. I'll show you diagrammatically that that would be inner. So we have the 3D orbital here. We have 4s, 4p. Okay, so the 3D is where we finish here, but then we have the 4s initially with no electrons in and the 4p with no electrons in. So if you like, if you're up for it, I can draw it here. So we could have 4s0, 4p0, just to see where the 3d, the 4s, and the 4p is coming from. So 3d, 4s, and 4p. Okay, and then we've got pairing. So these 6 electrons pair up. So we have Hunt, Pauli, Hunt, Pauli, Hunt, Pauli. They pair up. And now they leave space. Let's go with blue. They leave space for these orbitals to hybridize. So we've got 2 Ds, an S, and 3 Ps. So we've got 2 Ds, our S, and our 3 Ps, which is what we said makes it inner. And this is now free for the electrons from the lone pair on nitrogen to come in. So our lone pair electrons from nitrogen are going to come in. We have 6 of them. 3, 4, 5, 6. So these are the lone pairs from the NH3 ligands. And so on this occasion we form an inner orbital complex. Okay, let's look at another example which would form outer orbital complexes. So let's insert a new slide. Alright, let's go back to black. So we've just seen that a cobalt ion, Hexa Aqua ion, is an inner orbital complex. D2sp3. Let's compare that now with a nickel complex with the same ligand, NH3 6 2+. This is going to be an outer orbital complex. So this is going to be sp3 D2. So let's have a look. Again, we know that we've got nickel 2+. This is going to be D8. It's D8 because nickel has 20, just grab my periodic table. Nickel has 28 electrons. So we'd have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8. That would be nickel. Nickel 2+, we have to get rid of these 4s2 electrons. So that would just be nickel. If we want nickel 2+, we'd get rid of these. So we'd have 1s2, 2s2, 2p6, 3s2, 3p6, 3d8. And that's why we're saying it's a D8 complex. Now, in this occasion, although the ammonia was strong enough to cause pairing, here we notice that inner orbital complex is not possible. Let's see why. If we tried to rig it so that it was inner, let's see what happens. We've got our 3D, our 4S, and our 4P. So we're going to try and rig it. I've got 8 electrons to put in. Let's try and pair. So let's get our red pen. So Hunt, Pally, Hunt, Pally, Hunt, Pally, Hunt, Pally. There's my 8. And you can clearly see that there's not enough space now to add my 6 ligands. So the only thing I've got left now is D sp3. But I don't have D2 sp3. So it's not possible because I just don't have enough D's. Okay, so let's look at the alternative. The alternative in this case would be to have the alternative in this case would be to have SP okay. So I'm going to get my red pen. Okay, so this would, sorry, I haven't labeled the d orbitals. This would be 4s, 4p, 4d. So I guess I should have put my 3d on here. Yeah, let me relabel that because I forgot the 3d in the first place. Alright. So I've got my 3d, 4s, 4p, 4d. Let's go ahead and fill our d, not pairing this time, because that didn't work. So hunt, 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 hunt. It's 5. Pally, pally, pally. Okay, and then I've got my lone pair, so let's use blue. I've got my lone pair from nitrogen, and remember I'm going to hybridize these here to give my sp3d2. So I'm going to have lone pair, lone pair, lone pair, lone pair, lone pair, lone pair. So not only can I not afford to have this, if I did have this, which I can't, I would clearly have a diamagnetic substance because I have no unpaired electrons. But here I can clearly see unpaired electrons, so this would give me a paramagnetic structure, whereas this would have given me a diamagnetic structure. And more about paramagnetic and diamagnetic later, probably in another video. Okay. I guess for that matter, we can look at the previous slide. This would also be diamagnetic. Diamagnetic. Here, meaning we just have no unpaired electrons. Okay, so definitely I'd like my students to be able to explain this. You know, there's some nice go-to examples here that illustrate the point. Okay, let's look at another example. Two more examples, and that will segue us in nicely to look at titanium. So let's look at another example. Okay, let's look at nice cobalt example. So this example, so here fluorine has a negative charge. There's 6 of them. Overall, there's only a 3 negative charge, so it's really cobalt 3 plus. So this would be a direct comparison with our first example. So for that reason, let's tie them together. So let's start again by saying that whereas CONH3 was in an orbital complex, D2sp3 COF6 3 minus is an outer orbital complex, sp3d2. So let's have a look. So again, it's CO3 plus, which implies D6. I know my thing is thinking. It's never good when a computer thinks. Okay, so it's a D6 complex. If you're not sure why, I won't repeat it again, but I'll refer you back a couple of slides ago where we talked about why it's a D6 complex. Okay, so we have a D6 complex. However, the fluoride ligand is too weak. It's too weak a field ligand. It's too weak field to provide pairing energy. So we're not able to pair. So the 3D 4S 4P 4D. Let's go to red. So the 6 electrons we just have using Hund's first rule and Pauli exclusion, which is not what I've just done, because I'm talking and speaking at the same time, and I can't do that. Talking and writing, I can't do both. Hunt, 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 Pauli. And then my lone pairs are going to use sp3d2. So this is my S, 3 P's, and then 2 D's. They're going to go in here. And notice I'm left with something that again is paramagnetic. Okay, so I'm left with something again that's paramagnetic. Okay, so I think that's a nice contrast. So essentially, not always, but for the most part, one way you can tell, let's put it in another slide. So for the most part, for the most part, a paramagnetic complex in an octahedral field suggests, if it's paramagnetic, it would suggest outer orbital complex. sp3d2, whereas a diamagnetic complex in an octahedral field suggests an inner orbital complex, D2sp3. Okay, so that's something to keep in mind. It definitely can be used to argue evidence of. Okay, let's look at one more example, and that will allow us to segue nicely into titanium. So titanium Hexa Aqua ion. So we've got, well, titanium with 22 electrons. That would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. So I've now got titanium 3+, because the 3 positive charges land squarely on titanium, because water is neutral. Then I would lose the 4s2 and one of those. So that would be 1s2, 2s2, 2p6, 3s2, 3p6, 3d1. So we have a D1 complex, and this is why this ion is used very frequently, because it's a simple complex with just one. It's a D1 complex, just one electron to worry about. And this is going to form an outer complex. So 3D, 4S, 4P, 4D. Let's get our red pen going. Okay, so we've got the single D electron here, and then we've got the 6 water molecules. So we're going to hybridize these guys to give us our sp3d2 outer complex. And we know this is going to be paramagnetic. Lone pair, 6 multiples of lone pairs from the 6 water molecules. Oh, as I draw too many because I'm talking. Okay. And it's paramagnetic, obviously, because of this guy here. Paramagnetic means it has one or more unpaired electron. Okay, that will allow us to segue reasonably effortlessly into talking about some titanium Hexa Aqua chemistry. Which is what I would like to do now. Okay, so let's look at let's spend some time looking at this compound. This is a nice compound. Why blue? Why blue, universe? Who knows? Okay, let's look at this complex. Try and learn something by studying this complex. We may as well name it. It's the Hexa Aqua Titanium (3) ion. Hexa Aqua, it's got 6 waters, and it's a titanium 3 coordination compound. Let's look at the absorption spectrum. So if we look at absorption here against wave number, and this wave number is actually going to be multiples of 10 to the 3 reciprocal centimeter. So wave number has units of reciprocal centimeter, but in the scale I'm going to use, it's 10 to the 3rd reciprocal wave numbers. Let's try and make this a little bit better, a little bit neater. Okay, then we would have something like this, where we'd have 25,000. The peak would hover around 20,000, and we'd have about 15,000 over here. Again, it's 1,000 because it's by 10 to the 3. And this peak here, I want this to be around, or this is around 20,300 reciprocal wave numbers. Okay, so this absorption, a spectrophotometer would record this absorption. Remember, we have the 5 original, without any octahedral field, the 5 degenerate d orbitals. So this is our D1 of the free ion. But then this is split in the presence of an octahedral field to our EG level and our T2G level. So let's get our electron in here. So our D1 electron in the free ion. Our D1 electron in its ground state would go into the T2G, but it can transition to the EG. So this would be split by an octahedral field. Delta O. So the energy gap here would be delta O. And remember that this energy gap, delta O here, is energy, obviously, which is Hc over lambda, which is Hc wave number, which is numerically equal to 20,300 reciprocal wave numbers. And it represents the transition, e.g., from T2G to EG. Typically, you put the state that it arrives to on the left and the state that it comes from on the right, or the highest energy on the left and then the lowest energy on the right. Okay, so I'd like to quantify this because these units are funny units, so I'd like to convert them to a unit that's a bit more familiar. So I'd like to convert them to joules. That would be a goal. Suddenly cannot find my Joule calculation. Okay, so I'd like to convert that to Joule. So let's do that on the next slide. So is funny energy unit. So can we convert to Joule? Joule shouldn't be a capital letter. Obviously we can. So again, I'm using this equation. E is Hc over lambda, which is Hc nu with a twiddle on top. So this is just a dimensional analysis problem. Now, although wave number is a funny unit, it's the unit typically used in this type of science. But most chemists spend most of the training looking at joules, so then we hit this disconnect with the spectroscopy people that use wave number. So let's try and convert this to Joule. So we want Joule, so we should probably write Joule here. Well, I know that my Joule unit is going to come from Planck's constant. So we have 6.63 by 10 to the negative 34 Joule seconds. That's Planck's constant. That's just our input. I don't want to set it equal to something, but it's my source of Joule. I want to get rid of second, so let's have a reciprocal second in here. So we have speed of light, so we can write 3 by 10 to the 8 meter is equal to 1 second. So that's good, because then the second can cancel the second. Alright, so I've used Planck's constant, I've used speed of light. Now for the wave number itself. So the wave number is 20,300, that was the maximum absorption. And that was a number equal to 1 centimeter. Okay, so I want to get rid of that centimeter denominator. Well, I know there's 100 centimeter is equal to 1 meter. So I can cancel the centimeter and my meter will go back and cancel that meter. So the only unit that survives is the Joule, which is exactly what I want. So I know that if I run this calculation, this is 4.04 by 10 to the negative 19 joules. So we've just seen that 20,300 funny unit wave numbers is equal to 4.04 by 10 to the negative 19 joules. So it's useful to always get into a unit that you feel a bit more comfortable with. That's always a good thing to do. Yeah, let's spend the next few minutes looking at different typical values of octahedral field splitting. So let's call this typical octahedral splitting values. And we're going to use the funny, although common unit of wave numbers. Now we convert it to Joule whenever we want. Okay, let's look at chromium-3 complexes. Let's look at if we had 6 F- ligands, what if we had 6 water ligands, what if we had 6 ammonia ligands, and what if we had 6 cyanide ligands. Let's try and draw that there. We're looking at about, and we're not going to memorize these numbers obviously, we're just going to look for trends in the data. 15,100, 17,400, 21,600, 26,600. Okay, so we can see that as we go from left to right, the octahedral field splitting increases. And that's because as we go from left to right, let me label it in, so this would be the topic of another video, but we've got weak field ligands on the left, and then we've got strong field ligands on the right. Or we get stronger. So the stronger the field ligand splitting, the greater the split, the greater the energy separation between EG and T2G. Okay. So let's go back to our black pen. Let's have a look at cobalt. About 13,000, about 19,100, about 22,900, about 34,800, okay. Vanadium 3 plus, 16,100, 18,500. I don't have any data on that one. I have 23,400. Right, let's get a few more of these and then we'll see if we can identify any trends in the data. I have some pretty spotty data here on in. I've got iron 3. This will probably be our last one because it gets a bit spottier after this. Iron 3, I just have 14,000. I don't have any data for these guys. 35,000. Okay, so can we learn anything here? Well, we've got a spectrochemical series. That's what we can learn. So from looking at these field splittings, we can decipher the spectrochemical series, at least for first row transition metals. So we've got So let's see. We would have the, sorry, we would have, get my black pen back, we would have, the ones I have, the ones I have at least, iron 3 clearly splits the field less than chromium 3. Well, actually, I've got cobalt 3 is less than iron 3 is less than chromium 3 is less than vanadium 3. Okay? In terms of metals, and we can also see that F minus is less than H2O, is less than NH3, is less than Cn minus. So we get a table of, just by studying enough structures, we get to see patterns in the data, we can understand the patterns, and we can see that there's different combinations of metals and ligands that can split the field stronger than other metals and ligands. That will probably conclude this video, and we've just about kept it within an hour, so that's good.